So we now look at the problem of topological sorting. So far we have looked at depth first and breadth first search as strategies to explore all the vertices in a graph. But the graphs we have looked at have been undirected. In other words, if we have an edge of the form uv, then we can go from u to v or from v to u. So depending on how the depth first search or breadth first search brings us to u or v, the other vertex will be a child. Now we look at directed graphs. So a directed graph is one in which edges are actually oriented. So if we have an edge of the form u to v, there is an arrow pointing from u to v. So v is a child of u, but this does not necessarily mean that u is a child of v. So if we want to have u as a child of v, there must be a separate edge pointing back from v to u. So here is an example of a directed graph with 5 vertices a to e. So notice in this, for example, that A and B are connected in both directions. You can go from A to B and from B to A, but this requires two distinct edges, one in each direction. On the other hand, for instance, you can go from D to C, but you cannot go from C to D because the arrow is pointing from D to C. So as before, we can represent such a graph using an adjacency matrix or an adjacency list. So here is the adjacency matrix for this graph. So as usual, we have a 5 by 5 matrix, one row and one column for each vertex, and we enter 1 in an entry if there is an edge. So A to B there is an edge, so there is 1. A to C is 1. Similarly, B to A is 1. Notice that C has only incoming edges. So the row for C has no ones because there are no outgoing edges from C. D has two outgoing edges to C and E again has no outgoing edges, so its row is all empty. So in the empty rows are actually, the empty cells are supposed to be 0, but as usual we've only put a 1 and not the 0 to avoid cluttering up the matrix. So corresponding to the ones in the rows, we can set up an adjacency list. So A has edges to B and C, B has edges to A and C, D has edges to C and E, and the list for C and E are both empty because there are no outgoing vertices, so there are no edges leading out from C or E. So we can explore directed graphs in pretty much the same way as we explored undirected graphs. So let's look at how depth first search works on a directed graph. So as usual, we will start with the smallest vertex in alphabetical order. So we'll start with the vertex A. Now from A, it has two children B and C. So we will explore the smaller one first. So we're going to B. And now we recursively have to explore the edges out of B. So from B, we have an edge back to A, but A is already marked. So we can say that A is marked and B is marked. So B then adds an edge to C. Now we come to C, and now C has no outgoing edges, so we go back to B. B has no more outgoing edges, go back to A. Now A has an edge to C, but this is already seen, so we're finished. So now we have explored these three vertices. We go to the smallest unmarked vertex, which is D. Right? So D has an edge back to C, which we don't follow because C is already marked. Then we go down and we add E as a child of D. So this is what the basic DFS forest looks like for this graph. But now in this graph, it's interesting that we have more edges than more non-tree edges than the ones that we had in undirected graph. So the first non-tree edge that we discovered was the edge from B to A. So this is what we earlier called a back edge. Now when we came to A again after finishing processing C and B, we found that there was an edge from A to C. So C is a direct descendant of A, but we did not explore it, and that becomes now what is called a forward edge. So there is a non-tree edge from A to C, which is called a forward edge. Okay. Now notice that this would not have actually happened in the earlier case because we would have actually had undirected edges. Okay, so we wouldn't have this kind of situation in an undirected graph. And the third new edge that we find in this particular example is an edge from D to C. So this particular edge is a cross edge, right? So we have here a kind of cross edge. So when we do DFS on a directed graph, we have a similar procedure to the one we had for undirected graphs, but the non-tree edges come in multiple flavors. So in addition to back edges, we do have the possibility of forward edges and cross edges. For undirected graphs, we observed that we can examine the DFS forest and determine whether the graph is acyclic by looking for back edges. The same is true for directed graphs, although here we are not looking for arbitrary cycles, but what are called directed cycles. Cycles that we can complete by following edges in the forward direction and returning back to the vertex we started from. So it still holds that there is a directed cycle in a directed graph if and only if there is a back edge in the DFS forest. So here, for instance, A, B form a directed cycle because I can go from A to B and come back to A, and that is demonstrated in the DFS forest by this back edge back from B to A. And one can argue that if there is no back edge, there is no directed cycle. So though we do have these different edges, forward edges and cross edges, the cycle part of the graph, the acyclicity of the graph, depends only on back edges, just like for undirected graphs. So it's also important in this context to keep track of entry and exit numbers as we did for undirected graphs. So when we did the DFS for this graph, we started with A, so the entry number of A is 1. Then from A we started processing B, so the entry number of B is 2. Then we started processing C, so the entry number of C is 3. And then we found that there were no outgoing edges from C, so we finished processing C. So C exited first. Then we finished processing B, so B exited second. And then we finished processing A, so A exited third. At this point we switched over to D, so D was the fourth one that started, so its entry number is 4. Then we moved to E, so E was the fifth one that started. Then E finished, so E had exit number 4, and D finished, so D had exit number 5. What we will see is that these entry and exit numbers will actually be important when we start analyzing certain kinds of directed graphs in this section. So a directed graph without directed cycles is called a directed acyclic graph, and this is often abbreviated by the term DAG by taking the first letters of directed acyclic in graph. So DAG is a directed acyclic graph or a directed graph with no directed cycles. So it turns out that DAGs are quite useful for representing dependencies between tasks. So here is an example, for instance, where we look at a student who has to do 5 courses called C1 to C5. Now, some courses require other courses as prerequisites, and these are indicated by directed edges. So in this graph that we have drawn here, C3 requires both C1 and C2 to be completed before the student can take C3. Likewise, C5 requires the student to do both C3 and C4, but C4 in turn requires C3. So the student has to do first do C3, then C4, and only then do C5. C1 and C2 on the other hand have no prerequisites, so the student can start off the courses by doing C1 and C2 in either order. So it's quite clear why we need a DAG for such a set of dependencies. So these dependencies are feasible if and only if they're acyclic. If you imagine you had a directed cycle among the dependencies, then you would have, for instance, 2 tasks which depend on each other. So neither one of them can be done first because the other one has to be done before it. So if we have a cyclic dependency, then we have something which is infeasible. And so the interesting case is when the tasks are actually ordered as a DAG. So a natural question to ask when we are given a set of tasks with dependencies is to determine an order in which we can complete these tasks while respecting the dependencies. This means that if B depends on A, then we must complete task A before we complete task B. So if we look at the course example that we had now, we want to determine a feasible order in which a student can take these 5 courses so that each course is done after the prerequisites. So here, for example, we could start with C1 or C2. So let's say the student does C1 first. Now the student still can't do C3, but you can still do C2 because C2 has no prerequisite. So we can start with C1, then do C2. Now C3 is available because both the prerequisites are done, so we can do C3. And then, for instance, we have to do C4 before C5, so we do C4 and C5. Of course, so this was not a unique order because we could have done the first 2 courses in either order. So another possible sequence in which we can do these courses is C2, C1, then C3, then C4, and then C5. So in general, this problem is called topological sorting. So topological sorting asks us to list out the vertices in a directed graph in such a way that if there is an edge from A to B, then A must be listed before B. Now clearly, if a graph has a directed cycle, this is not possible because if we have a cyclic dependency, then we have 2 vertices A and B such that there is an edge from A to B, and eventually there is some edge from some other vertex, possibly B itself, back to A, and there is no sequence that is consistent with both these orderings. What we will show, on the other hand, in this lecture is that if the graph is acyclic, that is, if we have a DAG, then we can always efficiently compute a topological sorting of the graph.